Welcome to myprojectbazaar.com.
Let we discuss about our product title is Approximate Radix-8 both multipliers for low power and high performance operation. Let we see our product abstract. In our process we are going to approximate 12-bit multiplier based on the Radix-8 both algorithm are proposed. In our process the both multiplier consists of stage of multiplier encoding, the partial product generation, the partial product accumulations, the final additions. In our process the Radix-8 both algorithm, and we are going to the partial product in 9 type of the process are generated by the multiplier encoder. The partial product generator, moreover the tree is used to the implementation of the sum of the partial product to reduce the total multiplication time. The selections of partial product as input to the Wallace tree is controlled by the partial product generator. And then the determine the multiplier encoder, we go into the partial product generator and then input signals of 1s and 2 3 4 process. The decoding the process occurred in the Radix-8 algorithm in our 1 bit to multiply time and the corresponding the calculate the adder functions. The AND gate of select the partial product and perform the shift operations, while the XOR gate complete the inversions of the positive multiplies of the multiplicand negative factors. With using the 12-bit multiplier, the Radix-8 recording the algorithms generator 6 digit and the 6 partial product has generated. The process the inverting the partial products are accumulated by the Wallace tree. In this process the approximation of the adder and the 16-bit both multiplier through approximate designs of the proposed in the accumulation stage, and then the multiplier recording the result for that using the both multipliers has been widely used the high performance level and multiplications encoding the process. So consider 12-bit signed multipliers. The primarily addition is a process at the least significant bit for the same for x and y process are mean one input to another input sign bit for the process, because the sign does not change the multiplicand in the multiplied by the process. We use the only 12-bit of the middle of the process. The carry propagation of 12-bit adder takes the significant the time compared with the shifting to reduce the ripple carry propagations to adjustment bits process. Let we see our process flow diagram. In our process we have giving the 12 cross 12 bit multiplier in the input functions, and we go into the main blocks. The main blocks, the 24-bit multiplier operations will be performed in the multipliers. The basic gate logic or first design. Then to give the 12 cross 12 bit for input to the multiplier, we have designed the 144 AND gates designed, and by using the realization of gates the partial product generation will be done the performed 24 multipliers logics. As the result partial product generations, the 24 bits will be provided as output. Now we discuss the partial product generations. The process the both multiply has been widely used the high performance signed multiplications by encoding and thereby reducing the number of partial products. A multiplier using the Radix-4 algorithm is very efficient due to the easy to the partial product generations, whereas Radix-8 both multipliers is slow due to the complexity of generations, the add multiplies of the multiplicand in the paper process, and then the application of the approximate designs and 2-bit adder is designed for the calculations of sum of 1 and 2 of binary numbers. These adders require a small area and small low power but a short critical delay process. The 2-bit adder implementation of the less section of recording adder, the generation triple multiplications, no carry propagations. After we go into the or PR blocks. In our process, we consumed the 60 approximate Radix-8 both the multipliers designs, approximate recording the headers with the with and without the truncation of the process, the less significant bits the posted product, and the multipliers the fastest and more power efficient than the accurate both multipliers. The multipliers with the 16-bit truncation achieves the best overall performance in the process approximate the both level process. And then we going to use the D flip-flop for process for the 24-bit. In the 24-bit we split the 12 cross 12-bit multipliers after using the D flip-flop from the each and every bit from the single input. After going to the multiplier logic, in the multiplier logic we going to the simulate the process. Synthesis result we get the how much of complexity we reduce and power and area of process. The power efficiency accurate in the both multipliers, the we got the threshold logic process. Finally the approximate multipliers applied from the comparison blocks from the show the better performance of the approximate in the compared to both multipliers. After the fast and power efficient from the accurate and performance items for the hardware accuracies. Let me see our process running processor. In our process we have implemented the Xilinx 14.2 versions in the 12 cross 12 multiplayer process. First of all we going to the simulate the process. Just we are go simulation and which the main program we select, and then we going to the simulate the behavioral model. um, After running the process completed, automatically open the iSim simulator. We give the clock and enable and the write functions. We give the input and functions completed automatically running processor. We got output from the 24-bit process. The iSim simulator is open. We can give the input for the functions and the clock and the enable functions. We have already give the input in the programs. What are the input for the 12-bit and A and B two level inputs. After we go into the give the clock for the first clock. So leading edge value is 0 and trailing edge value is 1 and period 1000 ms. After completing this process, reset go into the give the force constant and then give it force to values 1 is a reset value. After this completing this, we go into the running the process. Just we run. After we go to the reset the process for 0. When we give the enable is 0, reset is 0, we got the output is full fledged. So other time we will not achieve the output results is fulfilled. So now we go to the run the process. We got the full output for the process. Each and every variable signals we get the output, and then just we give the input three type of clock signals. We just show the zoom functions. So this is a multiplies process. You don't get the process just like zoom the process. We got the result output for the 24-bit for multipliers to 12 cross 12 multipliers count the output for the 24-bit. So we complete the process simulation or completed. After we go into the implementation result. The implementation is must running the process for the synthesis report and implementation result. So the synthesis report we going to the running the process is completed. After we go into the implementation results also we should run the process. Here only we simulate the process, how much area is occupied and the power assumption. This results is considered from here only. Here we show the output for the device utilization summary. Here after completing the implementation design, we go into the detailed reports for synthesis report. At the same time for design summary for device utilization summary. Here give the result for the process, how much we using the slice LUTs process, how much use the logic, how much LUTs flip-flop pairs, and then flip-flop and user process and the IO bit. This process is very important for the LEDs, flip-top pairs, and IOB process. So this process completed, we go into the time process. So timing, how much time we give the time report, how much time we get the running the time for here. So it will be take the 12.598 nanoseconds, the full process completed. It will be take the IC that take the time for the this time 12.589 ns. Thank you watching our website.